Thank you very much. Good afternoon, everyone, and welcome to my talk, From Sequence to Success, making AI or using AI, the AI advantage to make protein design predictable. And I will cover a few different angles on the subject. I will start by introducing how we do protein design today and how we expect it to evolve into the future. And then I will kind of explain why we are at an inflection point today where AI can actually deliver value and make things much more predictable for us. I will also then give a case study, which will indicate that even for emerging modalities in the large molecule space, such as VHH, we can already deliver quite some advantages with AI today. So starting from the two key aspects that I want to highlight. One is kind of the way we work today. So already today, we introduce early developability screening to actually rule out candidates that do not translate into results in the lab later on. And we already rely on these short lab iterations or lab cycles to actually manage the risk that comes with protein design. The way we expect that to evolve into the future is to actually tie in silico developability predictive models as panels, essentially, so models that run on a computer, into these loops directly, and enabling basically to cut these kind of traps that you can fall into in the developability process out of the process by doing that. And then the other aspect I want to focus on is the things we actually design. So today the focus is very much on kind of established molecule classes. In large molecule space, these would be, for instance, antibodies, which I'm also going to introduce a bit. But there's already kind of an uptake of more emerging molecule classes, such as VHH. And here are some specific challenges apply that I'm also going to get into a little bit. And already there also we can have benefits from AI. So why do I believe that we are at an inflection point today where there is actually this transition from where we are today to where we will be in the future? There are three key drivers that I have identified that lead to this transition. One of them is scalable experimentation. So we are now able to actually do readouts at an increasingly parallel scale and actually do data acquisition at a frequency that is much more useful to build AI models than we were even recently. And this is still heavily evolving even now. In addition to that, we have richer representations. So we actually have a means to extract information using foundation models such as AlphaFold 3 or ESM for sequence data, evolutionary scale model. We have these models that actually allow us, even with a quite limited data set, to still draw insights from the data we have. And then thirdly, we get much better, and this is something I'm going to focus a bit on later in the talk, we get much better at actually tying what we learn on a machine in silico into the in vitro process that we actually do in the lab, and also tying what we learn in the lab back into building better models on the computer. And this integration is really key, in particular when you have to work in a quite low sample size regime like VHH design. Now, kind of zooming in a little bit into antibody specifically. I mentioned this is where a lot of action happens at the moment. So in antibody design, even today, we have to co-optimize. It is crucial that we kind of balance off mitigating these developability traps or developability risks, such as immunogenicity, such as thermostability, or such as self-interaction, or stability more generally, off against the activity we want the molecule to actually have. So it should fulfill its function, but also we have to be able to actually develop a given molecule. And the way that this is already being done now is through a better in silico in vitro integration. What that means specifically is kind of finding a trade-off or a sweet spot between actually having a molecule that has the desired activity and a molecule that you can actually develop in a robust fashion. In addition to that, the richer representations allow us to do this better by actually allowing us to predict ahead of time what will be potential developability traps for a given candidate, and therefore have much more success into the lab. And this is getting somewhat established. There are quite a number of approaches out there, and also some data sets in the public domain, although sample size is also limited for antibodies. Now, in terms of the more emerging classes of molecules, VHHs are very popular or very interesting, exciting molecule class because they are quite flexible in the design options that they allow you to take on. And basically, they are single domain antibody fragments, and they are very modular and can be engineered quite a lot. What that means in terms of benefits for the design process is that they are small in size, so they can actually penetrate much better, and that therefore also have an activity. Also, they have generally a very high stability potential, which also makes them interesting drug targets. However, as they are modular and fusible, this opens a lot of design options, but also comes with some complexity, which we're going to see in the challenges part. But you can have multi-mers of them, which is a very interesting property for a lot of design. However, they come with their own developability profile and constraints that make this design process more challenging. And one specific problem is the long exposed CDR3 that they have, which actually increases the risk of polyreactivity readouts. And we saw before, this is one of the developability risks that we need to mitigate against. In addition to that, they naturally have a very short half-life, which also means they cannot have the function you desire. And there are some extensions through this modularity components that you can apply that actually mitigate against this, but then you trade off some thermostability for it. So it becomes this trade-off game in the design process that you have to account for. And then finally, the hallmark of any VHH design is this translation between a camelid framework, where VHH are naturally found, and a human framework, so-called humanization. And this is a quite extensive process. There's a lot of literature on it. At the same time, this also comes with its own trade-offs because it can impair stability. So at each step of this, you can kind of fall back to your original candidate space and have to start over because you missed one of these developability traps. So to summarize, VHH design is challenging, and even more so than antibodies requires this early risk prediction. And this has to be accompanied with kind of smarter experiment choices because public data is very limited for VHH. And also, you have to start from a diverse set of viable candidates because there might be candidates that look good on some readouts but will not pass other gates. And also, if they're not viable, you cannot express them, you cannot experiment with them. So you have to start with a diverse set of viable candidates as well. Some of the challenges that you have to overcome to actually make a VHH design viable is, of course, the developability constraints I just mentioned on the last slide. That's the obvious one. And here I already outlined that we can now build some of these predictive models for these different properties and use them to actually mitigate these risks by flagging them earlier. But also we can have small sample sizes. There aren't big public data sets. Honestly, even for antibodies, things are limited, but definitely for VHH, there is quite a limit of labels out there that you can just leverage. And even what you can collect in the lab is typically going to be somewhat limited. So you have to be able to work in this kind of smaller sample size space in an effective way with AI. The solution we found, and I'm going to explain this in more detail on the next slide, is to use uncertainty-aware models. So to use models that not only report how good a candidate is going to do on a given developability element, so let's say how polyreactive the model expected to be, but also how uncertain it actually is about that prediction. And this uncertainty actually allows us to then improve the models as well. As we gather new data in the lab, we can actually incorporate that data to actually improve the models over time too. And this is called active learning. We're going to see this in action a little bit on the next slide. And then finally, the design space is vast, so vast that I could use any superlative that you want to describe it. So if we just start randomly selecting candidates in that space, we are probably never going to get to something useful. So you have to guide this process from a set of viable candidates that can be expressed, that are likely to have some of these properties. And there is also a lot of salt in actually proposing these good candidates. Now, kind of zooming in a bit on a case study. So the specific details of this are confidential, but I will try to describe as much as I can share in this audience to you. The general approach is to have kind of a loop system that starts from a generative model that is able to produce candidate solutions. These candidate solutions have to be kind of viable. They also have to be expressible, ideally, and you would want them to have kind of a function or activity that you are desiring as part of your research question. Then these models generate hypotheses. They can generate many hypotheses, can be in the millions. And then you want to actually know, okay, for these hypotheses that are generally viable, how do they appear to my property prediction model? So you want to train some models that can actually give you more information about what are the developability readouts going to look like? Is this going to have a polyreactivity risk for me? Is this going to have immunogenicity risks, etc.? So you want to then build these predictive models on top of foundation models like I mentioned earlier, for instance, ESM or AlphaFold 3. And you want to use these models to actually guide your prediction of the space. And these models should be uncertainty aware. So they should be able to report an uncertainty about their prediction too. These models will then assign kind of a likely readout for the properties as well as their uncertainty. And this combined information is used in an algorithm that trades off uncertainty and what we believe about a candidate currently and how promising it is for the different properties of interest. And then this gives us a ranking with some designs that we believe to be the most promising ones. And then we basically take these and run a wet lab experiment for the different dimensions that we are interested in. So we will study their activity, we will study their developability properties. And then the readouts of that can actually inform both our current lead candidate, so we can take out, let's say, the most promising design and make it a lead candidate for further experimentation, but also they will inform the models themselves. So they will also help us actually improve the models that we are building as part of the algorithm. And this kind of creates a flywheel effect, where the experiments actually inform better models, and the better models in turn inform better experiments or more promising experiments. And this is very powerful because it really speeds up the process and de-risks the process. Because at every point, you're essentially taking everything into account that you are interested in. And with every step, you are actually improving in 2 dimensions simultaneously. So this drives some important levers in terms of value for us. One key one is the faster cycle times that I just mentioned. So kind of speeds up the speed at which we can actually explore the space. And that is huge because the space is very large. So the more we can narrow down with the generative model and the more we can be efficient in what we explore, the better off we are for this very complex problem. In addition to that, we have an improved predictability. So we have a higher chance of success of a given design actually working out in the lab and not falling into developability traps, in particular at later stages, which is always going to be more costly. This also kind of reduces the time effort involved and makes the process more smooth. And then finally, all of that, of course, leads to reduced costs, both wasted effort in terms of people time and actually experimentation, but then also lab equipment that has to be used to actually run these assays. So in summary, this process kind of allows us to build a system that learns over time and improves itself over time and actually drives better and better candidates to the pipeline. So in terms of this specific system I've just shown, there are some things we've already proven and there are some things we're currently investigating. One thing we've been able to prove is that our generative engine is already delivering viable candidates, which is a very important starting point and actually allows us to narrow the space of where we're searching dramatically. What viable in this case means is they are nearly perfectly expressible. So any candidate that actually leaves the engine can be expressed in the lab and actually studied further. In addition to that, it includes already functional binders for the target we were interested in this project. And this includes also nanomolar hits, which basically are hits of the quality that you could manufacture directly in terms of the activity. What we've already done is kind of gotten some very strong in silico leading indicators. It's key how you measure things in silico to make sure that it translates into the wet lab. I will talk a bit about this after. But essentially, we're already planning kind of the validation of the entire loop. So we have the models built that can actually predict the different properties. We have some strong reasons to believe they will work well. And we are now investigating kind of how things improve as we move through the loop multiple times and drive these additional candidates to the system. And of course, we are also collecting the operational metrics, which is the actual, let's say, KPI improvement in terms of the value levers I have shown on the previous slide. Some key learnings on what actually makes such a program successful. I think one of the biggest things to highlight is still data limitations. This is true for antibodies still. This is even more true for VHH. The whole space is still very data limited. There are a lot of good efforts. I actually saw one come out just this morning called protein-based, which is also an additional data set. So there are a number of new data sources coming out. This is an evolving space. The field generally is moving in the direction of bigger public databases. But nevertheless, it's still a very data-limited space. And the data you can collect about a given modality you are particularly interested in is still going to be driven by your wet lab pipeline. What this means is that it's key also to explore and exploit. So exploring meaning kind of improving the models as you go. So also investing some effort in actually driving the uncertainty of the models down actively, which we are doing through this active learning, but then also exploiting the models. So actually using the models to find better candidates as part of the readouts. And balancing this and actually evolving this trade-off over time as you move through these loop iterations is quite a crucial aspect of a very successful program in this space. And then thirdly, I mentioned before, in silico leading indicators, I've seen many publications that give very promising outlook on methods, but when you look closely, they do not translate well to your specific problem. And what's usually the issue with these research publications where I found this to be the case is that they do not account for sequence diversity between their training and test data sets sufficiently. If these data sets are too similar to each other, then many methods can look very promising in spite of the fact that they are actually not going to deliver those results in your specific scenario. And this mainly comes from kind of not mimicking the wet lab distance sufficiently. So the diversity in your training test split has to mimic the diversity between the wet lab and your training data set correctly. And finally, but definitely not least, the most important point, in my opinion, is to have the right cross-domain talent blend. There are deep biological expertise needed to actually do this process effectively. At the same time, these are also very complex, in particular the uncertainty-aware modeling is a very complex machine learning problem as well. So it is key to have these like blended backgrounds. And this is something that we have in our company specifically selected people for, to have kind of both sides to their CVs by design. But also working with our customers, it is very key for us to kind of have a very effective communication across these domains, because we found this to be one of the most crucial elements of actually having a successful program. So what does all of this mean for you? If you are in the business of protein design, make sure to co-optimize early. Do not wait until you have a very promising candidate just to find it killed later on in developability readouts. In addition to that, validate incrementally. Do not make big leaps in one shot, but rather move step by step and find a way to incorporate some sort of flywheel process that actually drives better outcomes as you do these lab iterations. And then, when working with us, you will grow your internal know-how. So do partner with organizations that have a deep AI understanding and also come with a biology background, because they can also help translate the machine learning research to your team and also upskill your team. And you can keep the learnings and grow your internal know-how. This is a space that is still heavily evolving, but it is a very promising space that will have a big impact in the future. And just outsourcing it completely risks that your internal teams are not fit for the design process later on. If all of this resonates with you, then let's compare notes on your modality and essays, or have a general chat. We are right there at the booth 725. So you leave and you go to the left, you will be right with us. And I'll be very pleased to answer questions now and also afterwards if there's room for discussion. Thanks so much for your attention.